I'm going to talk today, quick introduction into stochastic simulation and discrete events. Both, I talk about COPASI, but both apply similarly to VCEL. So in COPASI and also VCEL, we are talking about biochemical reaction networks, which can span anything, can span genome, proteome, metabolome, or whatever you need. Especially in the genome and proteome, we often have low numbers of particles or species. Therefore, stochastic simulation is often called for. So in stochastic simulation, we see each reaction or process as a discrete event. Reactions are always only having a forward direction. And reactions fire with a probability which is depending on the substrates of that reaction. So K times the concentrations or numbers of the substrates. So how does stochastic simulation, how can you view it that in general? So first you analyze the system, you calculate all the probabilities of the reactions. Then you generate random numbers which determine which time the next reaction happened and which one of that. You update the system and you repeat. That's basically what a stochastic simulation is. In COPASI, I mentioned already, models are reaction networks, and you often have reaction network contains reversible reactions. So in that case, COPASI has a little tool which automatically splits reversible reactions in the forward and the backward parts and analyzes the kinetics of that reaction and does a split there too. That is possible for most kinetic laws. Sometimes it's not possible, and COPASI will need a little help. So after you have a model which has only irreversible reactions, you can freely choose the simulation method. It can be a deterministic one, a stochastic one, or a hybrid one. So after you have your model prepared, you can just switch the simulation algorithm and get the different results. In VCEL, you would create this application for the stochastic simulation. So here is just a simple comparison between deterministic integration and stochastic integration of the same. You see obvious differences. You have noise, especially in the stochastic one. You have this inner circle, which doesn't happen in the deterministic at all. So with that, I'm gonna go and switch to a small example. Let me see. And I take classic global model. Can you see this? Is that big enough?
Okay, yeah, I see it.
Good. So this is a very simple model. It has 3 species, 4 reactions, and we have just mass action. And we go to the time course. I can now choose any of the algorithm. Let's start with the deterministic one. Run. Let me move.
Maybe make those windows a little bigger.
Yes, I'm working on that. Start with that one. This one comes into effect later. Okay, that is a deterministic result. We see that the variable x increases from 250 to 550 or 570, and really doesn't matter how often I press run, the result will be the same. So if I now go to a stochastic method, and this is the Gillespie method called direct method in COPASI, and I press run, oh, this time it went from 250 down to, what is it, about 50. I press run again, this time it went up. So we see already a different behavior between stochastic and deterministic integration. So in this part, which this model actually illustrates, is that we have, for the stochastic simulation, two different attractors. One is around 50, and the other round is around 500 and something. So to analyze that, and for stochastic simulation, a single run is not really meaningful. So we could, in COPASI, use a repeat, and for that we use a parameter scan. I have that set up. I say basically I want to run the time course, and I want to repeat the time course 100 times. And if I now say run, you see that I get results. Some staying around 500 with noise, and the other one, yeah, let's say 80, something around that. And sometimes we have trajectories seeming to move between them, but going down, going up and down. Actually, if you run this for a longer time, you will occasionally see something switching from the lower solution to the lower attractor to the upper attractor. Okay, with that done, I'm gonna switch back to my talk. Okay, so in the example, we just used mass action kinetics. That is the traditional realm of stochastic simulation. However, in COPASI, we very early on expanded that for all kind of kinetics. The idea is that between reaction events, the kinetics do not change because the probabilities do not change because nothing happens. So in that case, we basically are able to convert any kinetics to something which is very similar to the mass action kinetics. And I think in VCell, we are currently exploring the same. I don't know if it's yet implemented. Okay, after that little side, I'm gonna switch now to discrete events. What discrete events are actions that change the model or the state of the system at a certain point in time under conditions you can define. Events were originally defined very early on in SBML and are both available in COPASI and VCell. Events have three main features. One is you need to define when they happen. You also need to define what needs to be modified. That can be variables or parameters of the system. There is an optional delay for an action, and I forgot, and you need to define what's supposed to happen to those parameters and variables. So how is that done? The first thing is you need to define when, and this is called a trigger expression. And events happen when this trigger expression changes from true to false. But from false to true, sorry. False to true, but not from true to false. So it happens in that example down here, which is actually the third one, where I have a sinusoid curve and my trigger is the rate should be bigger 0. That if you see there's an area where it's true, and at the peak of that oscillation, it changes to false. So this would lead to that this trigger is called at 10, 20, or 30, or 40, the points which are marked with the errors. Another example is I could compare variables of the system A and B. I could have a time-dependent one if the time is a certain value. So any Boolean expression basically can work as a trigger. The next thing is we need to define what changes we can have, and that is these things are called targets of an event. And an event can have more than one. Targets, as I mentioned earlier already, can be parameters or variables. If you change parameters like rate constants, you actually change the model itself. If you change a variable like species concentration, then you actually perturb the state of the model. And there is finally something, if you want to analyze system behavior, you can define quantities or probes that you can use to remember certain aspects at the time of your simulation, at the time of the event. So last not least, you need to define a new value for your targets. And that is an algebraic expression which can depend on any values of your model. These expressions are evaluated before the event happens. There are some nuances if you have delayed event when these are, but in general, it's always evaluated before the event happens. Okay, now let me go to a couple examples. I have a couple more minutes. Is that okay, Michael?
Yeah, I will try to be as quick.
Yeah, I just do one example. So this is actually a real model which somebody sent to us because it exposed a bug in COPASI's event handler. So if I look, it's model which has 12 species, 24 reactions, and it has one event which wants to determine the period. There is some oscillation in this model, and we want to determine the period of the oscillation. Maybe I delete this one. Scott. Okay, now we have it already open. We have one event which we want to observe the oscillation of the species PDP1N, and we want to, similar in that example I showed in my talk, we want to look at when the rate changes, becomes negative. So this event is basically triggered whenever PDP1 has a maximum. And at that point, we record the peak time of that event, so the time when this event happens, and we calculate the period of the event, which is the time minus the previous peak time. So the time between two peaks. Here it becomes important that these values are calculated before the assignment happens. So let's look at that result. What does that actually do? I run the simulation, and you see there are oscillations. Let me focus on the important things here. I said we wanted to follow the oscillation of PDP-1N. You see, it's not a regular oscillation. It's actually quite complex. And we wanted to look at the period. So here's the periods. And you can see whenever we have a peak, a new period length is calculated. When we see that the period length of the system actually switches. Okay, and with that, I'm going to be open to a couple of short questions, but maybe we should postpone that to later.